For the first time, scientists have created a qubit, not from regular matter, but out of antimatter. If you know anything about particle physics, you will know how groundbreaking this development is. A qubit, or quantum bit, is the basic unit of information for quantum computing. Unlike a regular bit, which is either 0 or 1, a qubit can be both at once through a property called superposition. At CERN, the world's largest particle physics laboratory, researchers managed to hold an antiproton in a quantum superposition for nearly a full minute. That might sound like a technical detail, but in the world of antimatter, it's a groundbreaking achievement. Antimatter is the mirror twin of regular matter, identical in mass, but opposite in charge. When the two meet, they annihilate each other in a flash of energy. This makes it incredibly hard to store and manipulate. And yet, the base collaboration at CERN has done it, suspending an antiproton in the fragile quantum state where it exists in two opposing conditions at the same time. This isn't about building antimatter quantum computers. Ordinary matter qubits are far easier and safer to work with for developing computers. What this experiment really does is give physicists a new and precise way to probe one of the deepest mysteries of the universe. Why does the energy and matter in our universe even exist? According to everything we know, the Big Bang should have produced matter and antimatter in perfectly equal amounts. If this had happened, they would have annihilated each other completely, leaving a universe with no stars, no planets, no you or me, just energy. And yet, here we are. In a universe dominated by matter, somewhere, something tipped the scales. Physicists call the delicate balance between matter and antimatter CPT symmetry, charge, parity, and time. It says a particle and its antimatter twin should behave exactly the same under all physical laws. So far, every test has confirmed this balance. Antiprotons fall in a gravitational field, the same as protons. Their mass is identical. Even their behavior in magnetic fields is indistinguishable, with differences undetectable down to parts per billion. Previous experiments showed no cracks in this symmetry, and yet the universe clearly chose matter over antimatter. This paradox has haunted physicists for decades. By creating an antimatter qubit, scientists now have a tool to look even deeper. Holding an antiproton in superposition means they can study its quantum properties with far more sensitivity than before. Superposition allows a particle to exist in multiple states simultaneously. It's like a coin showing both heads and tails at the same time, at least until you actually look. That means the antiproton can spin both ways at the same time, making it act like a quantum bit or a qubit. Quantum states like this exist for only very brief moments. They break down almost immediately when they come into contact with the outside world. Holding it stable for 50 seconds is a record for antimatter, and it opens the door to testing it at a level of precision we've never had before. The implications are enormous. If matter and antimatter differ in even the smallest hidden way, too subtle for past experiments to detect, this method might finally expose it. That difference, no matter how tiny, might explain why the universe didn't self-destruct in its first moments. It might even point to a realm of physics that lies beyond our current standard model. But even after they complete their tests and still find nothing, that result would be just as profound. It would mean that the imbalance that gave rise to the universe has an origin even stranger and deeper than any theory we've yet developed. Either way, this kind of experiment forces physics to its limits. What makes this even more exciting is what comes next. The base team is preparing a portable system called Base Step, which will let them take trapped antiprotons out of CERN's noisy environment to quieter, specialized labs. Why does that matter? Magnetic fluctuations at CERN can interfere with the ultra-sensitive measurements they need. A quieter lab means cleaner data and longer quantum coherence times. maybe 10 times longer than they've achieved now. By advancing precision even further, we may finally detect a deviation in CPT symmetry or verify with greater certainty that matter and antimatter are fundamentally identical. It's also a stepping stone to even more exotic antimatter experiments. If we can control the quantum states of antiprotons, why stop there? Anti-hydrogen, the antimatter version of the simplest atom, could be next. It would allow scientists to test whether antimatter responds to gravity in the same way as matter, or if there's an unexpected difference. It could also probe how antimatter responds to fundamental forces in ways we've never been able to before. This highlights why the successful antimatter qubit experiment is far more than just a proof of concept. It may be the first step into an entirely new realm of physics. It's a tool for peeling back the most fundamental layer of reality. Antimatter isn't just exotic fuel for science fiction starships. Antimatter is supposed to be a perfect mirror of matter, but something in that reflection is off. And if we can find that difference, we may finally understand why the universe chose to exist instead of annihilating itself into nothing.